We're continuing our discussion of comparison tests. In the last video, we talked about direct comparison. Today, we're going to be talking about the limit comparison test. And so this limit comparison test requires you to kind of know something about one of the series. That is to say that if one of the series converges or one of the series diverges, and if you find the limit as n goes to infinity, and the limit happens to be both positive and finite, then they either both converge or they both diverge. Okay, so you have to know something about one of the series in order to make a conclusion. All right, so we're going to take a look at an example. All right, we're going to be looking to see if 1 over 2 to the n minus 1 either converges or diverges, and we're going to compare it to something very close to it. That is 1 over 2 to the n. All right, notice there's a difference. It's off by 1. Okay, it's off by 1. It's 1 less in the denominator, in other words, not off by 1. 1 less in the denominator. All right, so if you want to think about it, say one of them is 1/4 and the other one is 1/3. You know, something along those lines. All right, so what we're going to do is we're going to do the limit comparison test to figure this out. Well, the first thing that I want to say right here is that 1 over 2 to the n converges. All right, and how do I know that it converges? Because it is a geometric series with r equal to 1/2. And since r, and they always say the absolute value of r, is less than 1, we make the claim then that it converges. So what we're going to do is we're going to take the limit of one versus the other. And if we find that the limit is both positive and finite, then we can say that this guy right here converges because this guy right here converges. All right, so that's what we're going to do here. All right, so let's take a look at this example. All right, let's find the limit as n goes to infinity. All right, of 1 over 2 to the n, not 2n, 2 to the n, minus 1 over 1 over 2 to the n. Okay, so we do this right here. We keep, flip, and change. We end up with the limit as n goes to infinity of 2 to the n over 2 to the n minus 1. Okay, and as n goes to infinity, all right, what we need to do here is what we're going to do here is we're going to divide everything by 2 to the n. Okay, so we're going to divide this by 2 to the n, divide this by 2 to the n, divide this by 2 to the n. We're going to factor it out, in other words. All right, so we're taking out this common factor. We're going to be left with some limit that looks like this. The limit as n goes to infinity of 1 over 1 minus 1 over 2 to the nth. Okay, so right here we end up with this right here going to 0. We're left with 1. Well, what can you tell me about 1? 1 is positive and it's finite. Okay, it's positive and finite. So what's the conclusion that we can make? Well, 1 over 2 to the n converged. So 1 over 2 to the n minus 1 converges. So therefore, we make that conclusion. We say therefore, the series n equal 1 to infinity of 1 over 2 to the n minus 1 converges since, and I already stated it, but I'm just writing it down now. That's a funny looking sigma. Since from n equal 1 to infinity, 1 over 2 to the n converges. All right, and there's really nothing more to it there. All right, and we'll go ahead and take a look at a couple more examples. All right, so let's take a look at the next ones. So we look at the next one. It says, given some example, it says S is some series from 1 to infinity, 2 to the nth over 3 to the n minus 1. It says, what series can we use to perform the limit comparison test and determine if it converges? All right, so this one's not too bad. What we're going to do, let's write out, let's say, what we call a sub n. And a sub n is this guy right here given in our problem, 2 to the n over 3 to the n minus 1. Well, what could we pick? All right, what could we pick? Well, let's pick a b sub n. That's very similar. How about 2 to the n over 3 to the n? That's close enough. I'm going to factor out that n power, though. I'm going to say it's 2/3 to the nth. Okay? 2/3 to the nth. Well, what I can say here is that my factor, my r, equals 2/3. And since r, the common ratio, is less than 1, I can make the claim that this one right here converges. All right, so I know that already. All I need to do is find the ratio and find the limit of these two, a to b. And if it's positive and finite, then S must converge. All right, so let's go ahead and do that. We have the limit then as n goes to infinity of 2 to the nth over 3 to the nth minus 1 over 2 to the n over 3 to the n. All right, this is the limit as n goes to infinity of what ends up happening. The 2 to the n gets rid of itself. 3 to the n over 3 to the n minus 1. And very similarly in the last example, we end up with a limit that looks like this. The limit as n goes to infinity of 1 over 1 minus 1 over 3 to the nth. This little term down here goes to 0. And we're left with, again, 1, which is both positive and finite. All right, therefore, what can we say? S must converge. S converges. All right, so we can make that claim right there, that assertion. All right, and I think it's good for us to take a look at one more example. All right, so it says here we're looking at some series 2 to the 2n plus 5 over n minus 3 times n minus 2. We're looking at this series from 1 to infinity. I just did the algebra for you in the bottom. I multiplied, I did the binomial expansion, so it just changes to n squared minus 5n plus 6 in the denominator. We should use something like 1 over n. Okay, because if you think about it, 2n over n squared, if you're just looking at those initial leading terms, you end up with something like 2 over n. So 1 over n, the harmonic series, is a good one to look at. So what we're going to do is we're going to take the ratio of one to the other. And if we take the ratio of one to the other here, if it's positive and finite, then the 2n plus 5 over n minus 3 times n minus 2 diverges. All right, so let's go ahead and take a look. We look at, in this case, the limit, and let me switch my pen color here. The limit as n goes to infinity of 1 over n divided by 2n plus 5 over, and I'm just going to write it with its binomial expansion. It's a little bit easier to look at. Minus 5n plus 6, okay? We keep, we flip, we change. What does this look like? The limit as n goes to infinity, we end up with, n squared minus 5n plus 6, and it's going to be divided by 2n plus 5, but then you're multiplying by this 1 over n, so then this becomes n squared, and this becomes 5n. That's what happens with the 1 over n. It's multiplied by that denominator. All right, so what we're going to do here is we're going to divide everything by this n squared. All right, and if you remember, you know, in another video somewhere when we're talking about limits at infinity, and I've mentioned it before, Bobo Botno eats DC. This is how you can treat those limits at infinity. Bigger on bottom, 0. Bigger on top, the limit does not exist. But if the exponents are the same in terms of the leading coefficient, then divide the coefficients. So you end up here with a 1, right? This, you end up with a 2, all right? As n goes to infinity, this is going to go to 0, this is going to go to 0, this is going to go to 0. All right, so what ends up happening as n goes to infinity, you're left with 1/2, which is both positive and finite. And since it's positive and finite, okay, what can we say? Well, we compared it with the harmonic series. The harmonic series diverge, so S in this case, in this example, diverges. All right. So, as always, I hope this video was helpful. And remember, like and subscribe.